In this second part of our organizing data video, we're going to look at histograms, bar graphs, and frequency polygons. First thing we want to do is make sure we know what a histogram is. A histogram measures frequency. It's used for continuous values, so the bars do touch. So what that means is, think about heights. Heights are not discrete. Heights do not jump from, it's not, you're either 5 feet or you're 5 foot 1 inch. There's nothing in between. There is something in between. I could be 5 foot and half an inch. I could be 5 foot and 1/4 inch. I could be 5 feet and 3/16 of an inch. So it's a continuous scale that you can go through all the way through all of the possible values. So think about as you're growing, you hit through every height from your birth height to your finalized height as an adult. So that would be considered something that's continuous. And oftentimes our continuous values are things like times or measurements, things like that. Because it's continuous, our bars in a histogram will touch because from one value to the next value, there's not a jump. And so therefore, our bars will need to touch when we do a histogram. So we are going to make a histogram values that we had in the very first example. And so remember we had talked about our class widths before, where we were using class widths of 2, so from 66 to 67, 68 to 69, etc. Take a moment and draw the scale for the frequencies and also for my class widths. So I'm going to pause and draw that on there. You might want to try drawing your own and then compare. So here I'm going to label the bottom as heights, and then this side on a histogram is always going to be the frequency because it is a graph that shows frequency. And so then we look at our values. So again, for 66 and 67, there were 4. So that comes up to here, and I'm making my bars 2 bar widths. 68 to 69, there were 2. And you don't have to use different colors. I just really like to color code. And then 70 to 71, there was 6, 7, 8. So it comes up to here. And again, my bars will need to touch. Then we have 72 to 73. That's 7 plus 4 is 11. So that's halfway between 10 and 12. Boop, boop, boop. And then for the last one, we had for 74 and 75, there were 3. And so this gives us a histogram. Again, the bars do touch because you're dealing with a continuous value, a continuous spectrum. The next graph we're going to look at is a bar graph. A bar graph also measures frequency, how many times a choice is selected or a height shows up, or etc. But it's used for discrete values. So those are values that are different from one another and not continuous. So an example of this, we're about to see an example that involves people's favorite fruit. So the objects in the bottom are not connected to one another. So an apple is obviously not the same as a fruit, it is a fruit. An apple is not the same as a banana, and there's not like a continuum. Like, can you be halfway between an apple and a banana, like a banana? I don't know. Well, you can't. So those things are considered to be discrete. So therefore, the bars do not touch in a bar graph. So histogram, bars touch. Bar graph, bars do not touch. Okay, so we're asked to make a bar graph representing the class result of favorite types of fruit. Now that's funny because we are not meeting in class. Typically, if we were meeting in person, I'd say, okay, everyone, whose favorite fruit is citrus? And make sure you only vote once. Whose favorite fruit are berries? Whose favorite fruit are apples, bananas, or something else? And because we're not in class, we don't get that same experience. So we're going to use previous data of a previous class of mine. So when I asked this question before, we had citrus, and I had one person say that they like citrus. For berries, I had 7 people say that their favorite fruit were berries, like strawberries, raspberries, blackberries, blueberries, any of those. I had 6 people who said that their favorite fruit were apples, bananas. We had 11 people say that their favorite fruit were bananas, and then other, I actually had nobody say other. Apparently, everyone likes either citrus fruits, berries, apples, bananas. So, what we then do is we create a scale and we label our values along the x-axis, which will be labeled with the types of fruit: citrus, berries, apples, bananas, and other. And so along the x-axis, we have our types of fruit. And then along our y-axis, we have the frequency, or how many people voted for that. You could label it either way. And then we make our bars. Now, because these are discrete values, they do not touch. So notice how I gave a space in between each one. So for citrus, it's 1, which is halfway between 0 and 2. For berries, it was 7, which is halfway between 6 and 8. Notice that my scale on my y-axis goes by 2s. So there's berries. Apples was 6. Bananas, which I made yellow on purpose, was 11. Also, bananas are my least favorite fruit. I actually don't particularly care for bananas. It's a consistency thing, not a flavor. The flavor doesn't bother me. Not that anybody asked, but just so you know. And then other, if I had been asked, I would have been in the other category because my favorite fruit is actually pineapple. But anyway, I wasn't asked. So I will put other there, even though there were 0 values, and I might darken the bar on 0, just showing that there was nothing there. So there we go. This is a bar graph that's representing the data from a survey. So when we think about the differences between a bar graph and a histogram, we know that histogram, the bars touch because we're dealing with continuous data, often and mostly numerical data, whereas a bar graph, the bars do not touch and we're dealing with discrete, separate things. Okay, so which would be appropriate for qualitative data like eye color? Well, eye colors could be brown, they could be blue, green, hazel. There's more, and I can't even think about it. So that would be things that are discrete. Okay, your eyes are either brown or blue or green or hazel. And then something quantitative like grades, well, I could have a grade that's like 87.5 or 62.3. Hopefully not a 62.3. But we have this idea of if it's a continuous value that's quantitative, we would use something like a histogram. And if it's something discrete and qualitative, you would use a bar graph. So a frequency polygon is another graph that we can use to represent the data. They are line graphs with scales that are the same as those of the histogram. So essentially, the horizontal scale indicates observed values and the vertical scale indicates frequency. So to make a frequency polygon, you actually just place a dot at the corresponding frequency above each of the observed values. And then you connect the dots with a straight line segment. When constructing the frequency polygons, you will also want to put in 2 additional class marks, one at the lower end and at the upper end on the ends of the horizontal scale. And I'll show you what I mean by that. Since the frequency at these added class marks is 0, the end points of the frequency polygon will always be on the horizontal scale. So one thing you need to know about a frequency polygon is that you want to put the dots, because we're going to be essentially connecting dots, the dots need to be at the midpoint of each class. So dots at the midpoint. Also, that very verbose way of saying what I was saying is just that it needs to start and it needs to end at 0. I put a little picture of the histogram that we made before in the top right corner just so that I can use the values and keep track of that. But the scale on this frequency polygon is actually going to be the same. Okay, so we need to start at 0. We need to end at 0. So at the beginning of my frequency polygon and at the end of my highest upper limit, we're going to put our dots on 0. And then at each of our midpoints of where our bars would have been, we put a dot. So for 66 to 67, it's going to be at 4. So the midpoint would be right here. At 68, the class 68 to 69 was at 2. So the midpoint is right here because this is the bar that we're looking at. For 70 to 71, the midpoint would be at 8. For 72 to 73, the midpoint, we would put the dot at 11. And then we would put our last dot in the midpoint for the range 70 to 75, which was at 3. And then we just connect each of these dots. So starting from 0 on the left, we go up to 4, down to 2, up to 8, up to 11, down to 3, and down to 0. And this is our frequency polygon. Now it's a polygon because it is a many-sided shape. It's not convex, but it is a polygon. If I fill this in, it would look like a shape. I mean, it is a shape. It's the outline of a shape. But I could fill it in and you could see a very beautiful polygon. So we're going to see this example number 6 where it gets cut off, but we're going to look at the wording of the question first. It says a group of test grades are shown below. Make a stem and leaf plot for the data and answer the following questions. How many F's were there? How many A's? What was the most common grade? And what is your overall impression of their performance? List the grades off to the side. You should have them on the guided notes in front of you. Mine got cut off of that previous slide. Okay, so first we need to recognize what a stem and leaf display is. I call it a stem and leaf plot, but the book does call it a stem and leaf display. So I'll try and keep consistent, or might just say stem and leaf. It's a tool that organizes and groups the data together, but it allows you to see the actual values that make up the data. So you don't have to, in a histogram, that information kind of gets lost because anything in our previous example that would have been between 66 and 67 gets lumped together, so you don't see the individual values anymore. But in a stem and leaf display, you still see those values. To construct a stem and leaf display, each value is represented by 2 different groups of digits. The left group of digits is called the stem. The remaining group of digits on the right is called the leaf. There is no rule for the number of digits that must be included in the stem. Usually the unit digit is the leaf and the remaining digits are the stem. So for example, if we had a number like 72, the 7 would be the stem and the 2 would be the leaf. Okay, so then you add all the leaves for all the values that have the same stem on the right. I know that that sounds interesting or weird, but I'll show you how this works. So looking at these grade values, they go from a range of 47 is the lowest and the highest is 102. So my leaves are going to all be my digits to the left of the ones digit. So it's going to start with 4, 5, 6, 7, 8, 9, 10. Those are all of my stems. Separate our stems and leaves with a vertical line. And then what we do is we write all of our leaves, which are all of our digits, in order with where they go with the stems. So for example, the only value that we have with a 4 as a stem is 47. So behind the line, we would put the 7. But when I look at 50, or the stem of 5, we have 57, 58, and then let me scan, see if there are any more. No, so we just have a 57 and a 58. And so our leaves would be a 7 and an 8. We show repetition in stem and leaf plots or stem and leaf displays. So if we had like 57, 58, 58, we would need to make sure that we put 7, 8, 8. But in this case, there is only one. We'll see examples with repeats later. So let's look for anything that has a 6 as a stem. So anything in the 60s. We have 62, 67, 63, 63. We got a repeater right there. And that looks like everything that has a 6 as a stem. So we're going to put those in order. So it's going to be 2, 3, 3, 7. Okay. Then let's look at everything with the 7s as a stem. So we have 77, 79, 70, 75, and 74. So let's put those in order. I'm actually going to circle those again in another color just so I can keep track of them and the order. So we have a 0. We have a 4, a 5, a 7, and a 9. Okay, let's do the same thing with our 8 stems. So anything in the 80s we would use. So 81, 87, 80, 83, 88. That's all of them. So in order from least to greatest, we have 0, 1, 3, 7, and 8. Then we're going to do everything in the 9s with a 9 stem. So in the 90s, 96, 93, 91, 91, 96, 93, 96. So the lowest is 91, and there's 2 of those. So 1, 1. Then we have 93, 93. Then we have, so I counted that one, and I counted that one. Then we have 96, 96, 96. So there are 3 6s. And then our last stem is our 10. So anything in the hundreds would be that. We have 100, 100, and 102. So 0, 0, 2. And this represents our stem and leaf plot of these grade data, the grade data. So the nice thing about a stem and leaf plot is that you can really kind of see the shape of the data. The majority of people did the majority of people got scores in the 90s. Okay, and overall they did pretty solid. But then we have to answer these questions. So the first question, how many Fs were there? An F is anything less than 60. So that's going to be these right here. So there were 1, 2, 3 Fs. How many A's were there? Well, that's anything that's 90 or higher. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The most common grade is the grade that showed up the most frequent times, number of times. So you would want to look in each row and figure out which one had the most repetition of the same value as leaves in that row. And so that gives us 96. Or we could also say, if we're just talking about letter grades in general, we might say that it's the A's were the most popular. I'm down with that, or the 90s. What is your overall impression of their performance? I would say overall they did quite well. More than half of the students got a passing grade. That's a solid spread. I wouldn't be mad at that if that were an example of our grades. I don't want you to get 47s though, but I wouldn't be mad if that's what the spread looked like. The last graph we're going to look at, and I'll try to keep this brief because I know the previous video was long as well, and this one's getting long as well. But we're going to look at the last graph, which is a pie graph or a pie chart. And a pie chart is broken up into percentages. The percentages must add up to 100%. If there's a discrepancy with the responses, they have to alert you. Like if it doesn't add up to 100% for some reason, they need to tell you why. But in this example, we have 800 people who attended a Ringling Brothers and Barnum and Bailey circus were asked to indicate their favorite performance. The circle graph below shows the percentage of respondents that answered tigers, elephants, acrobats, jugglers, and other. Pie charts often have other to account for getting up to 100%. Determine the number of respondents in each category. So what we essentially do is we know how many total people there were, 800. And so to find out how many people responded in each category, we would take the percentage from that category, rewrite it as a decimal, and then we multiply it by 800. So if I want to figure out how many people like tigers, I would take 38% and write it as a decimal and multiply that times 800. Same thing for elephants. I would rewrite 26% as a decimal and get how many people liked elephants. Same thing with acrobats and same thing with all of them. So I calculated all of those values. I've written the answers there so you can check them yourselves. One thing you should note though is that if I added all these values together, I should add up and get a total of 800 because there were 800 people who were surveyed. So if I were to add 304, 208, 136, 112, and 40 together, I should end up with 800. And that concludes our organizing data lesson. There's a lot of different ways we can represent data, and so you kind of have to parse through and figure out what's the best way to represent the information that would give an accurate picture of what's happening and kind of honor the type of data that you're looking at. So that's the idea of critically picking whether I should use a bar graph or a histogram, whether I should use a frequency polygon or a stem and leaf plot, whether a pie chart would be best, etc. So please start working through your homework for 12.2, and if you have any questions, be sure to email me and ask.